Welcome, focused learners, to today's Explainer. I am absolutely thrilled to guide you through this session because we are jumping straight into the foundational building blocks and dynamic movements of grade A geometry. We're going to take those abstract rules of shapes and space and make them completely concrete. Okay, let's dive into this. Here is the roadmap we'll follow. The building blocks, common geometry misconceptions, rigid transformations defined, modeling rigid transformations, pause checks and reasoning, and finally, a recap and transfer question.
Section 1. The building blocks. Let's formalize something we see every single day. A line. Put simply, it's a straight path that extends infinitely in both opposite directions. The absolutely crucial concept to grasp here is that a true geometric line has literally no starting point and no stopping point. It just keeps going and going forever.
Building on that idea, a line segment is simply a part of a line, but unlike a line, it is bounded by two distinct endpoints. And because it has these specific start and stop points, a line segment is actually a measurable piece of geometry.
So the big question is, what happens when we place lines together in a plane? Well, that brings us to parallel lines. These are lines that never ever intersect, and they are always the exact same distance apart. Honestly, no matter how far they extend into infinity, there's just no way they'll ever cross paths.
Now, on the flip side, we have perpendicular lines. These are lines that intersect in a very, very specific way. They cross each other to form exactly right angles, or perfect 90-degree angles.
Section 2. Common geometry misconceptions.
Before we start moving things around, let's address this first misconception directly. The myth is that a ray has two endpoints. Actually, scratch that. The fact is, a ray is a directed line segment that consists of exactly one endpoint, and from that point, it extends infinitely in one single direction. You can kind of think of it like a laser pointer extending forever from a single source. Here's our second myth. An angle is just one bent line. Nope. The actual fact is that an angle is the union of two distinct rays that happen to share a common endpoint. That shared endpoint is what we formally call the vertex of the angle. Our third myth to bust is the idea that every sketch you see is perfectly to scale. In reality, geometric sketches are just visual models. They're often not drawn to exact scale, meaning you can't just trust your eyes to measure lengths or angles. You've got to rely on the mathematical properties and labels provided to you.
Section 3. Rigid transformations defined.
This is where the action happens. Our first rigid motion is a translation. A translation is simply a sliding motion. It slides a figure to a new position on the plane without rotating it and without flipping it. The whole shebang stays facing the exact same way, just in a new location.
Next up, we have a reflection, which is a flipping motion. It literally flips a figure across a specific line to create a perfect mirror image of the original object right on the other side.
Finally, we have a rotation. A rotation is a rigid motion that turns a figure around the fixed center point, much like a wheel turning on an axle.
Section 4. Modeling rigid transformations.
Let's actually put this into practice. Step 1, we start with our explicitly labeled created figure. For step 2, our first transformation, we translate or slide the figure to a new spot. Then for step 3, our second transformation, we reflect that translated figure across a line to create a mirror image. Now, the absolute most important rule of rigid motions is step 4. Notice that the original lengths and the original angle measures are strictly preserved throughout both of these transformations.
Section 5. Pause checks and reasoning. Here is pause check 1. If a line segment is rotated 90 degrees, does its length change? I want you to explicitly pause the explainer right now if you need a moment to think about this question.
Okay, the answer is no. The logical reasoning here is that rotations are rigid transformations. By definition, a rigid transformation means that all segment lengths, as well as angle measures, are strictly preserved. The object moves, sure, but its size and shape do not change.
Let's try pause check 2. True or false? The two sides of an angle are considered two lines. Once again, please pause the explainer to evaluate this statement based on our earlier myth busting.
And the answer is false. The reasoning is that an angle is formally formed by the union of two rays, not lines, sharing a common endpoint which we call the vertex. Remember, lines extend infinitely in both directions, whereas these rays start at that exact shared vertex.
Section 6. Recap and transfer question.
Foundational objects like segments, rays, and angles are the building blocks of geometry. Rigid transformations, translations, reflections, and rotations move these figures through space. These specific transformations always preserve the original lengths and angle measures of the figure.
If you translate a created figure and then rotate it, how do you know the final figure is perfectly congruent to the original?